Hello, we are SCUDEM Team 1109 from the United States Military Academy. My name is Masen Turner.
My name is Wiltz.
And I'm Landry Lee, and this is our project.
We chose Problem B, punishing infants. In a study conducted by researchers Kinkobi et al., they found that infants as small as 19 months old exhibited punishment towards other infants exhibiting antisocial behaviors. Yet the question arises, can this behavior be replicated not only in infants, but in older and bigger populations in the real world? In order to answer this question, we developed a model based on a modified Locke-Voltaire predator-prey logistics model to display different populations and their tendencies to react to antisocial and aggressive behaviors. Additionally, we analyzed how different types of corrective actions, such as reinforcement, affect these same populations' propensities to act out against those exhibiting antisocial or aggressive behavior. For our model to make sense, there are some key assumptions that are necessary to dictate the propensities of these different populations. Firstly, the punishment inflicted on the population that is exhibiting aggressive behaviors affects each person in that population all the same. This way, the spread of punishment does not vary within the population. Secondly, each population acts as that population entails. Therefore, if one population is said to be punishing another, they must be punishing, and if they stop punishing, then they become a part of another population exhibiting another behavior. Third, the total population stays constant throughout the entire process. Since later we will be displaying some populations as percentages of the initial population, the total population must remain constant so that it does not disrupt our model's variables and results. Lastly, time is a variable used to predict and behavior rather than specific time increments. This is because there is not enough data, and the goal of the time-population relationship is not to measure how long it takes for these populations to shift. Rather, it is to see how populations change in response to specific behavior. To transform this real-world problem to a functioning model, we defined our variables and parameters. For our independent variable, we use time, whose units are insignificant so long as it can only progress in a positive direction. For our dependent variables, we have three different populations. Population 1, which is represented by x of t, is the population that punishes antisocial behaviors at time t. Population 2, which is represented by y of t, is the population that exhibits antisocial behaviors at time t. And population 3, which is represented by z of t, and is a neutral population who neither punishes nor exhibits antisocial behaviors at time t. Moving on to our parameters. To create multiple situations in which we could show these populations' propensities to affect each other, using social norms, we used constants k1, k2, k3, and k4. We also established population limits, L1 and L2, to ensure our populations do not go negative or past 0. Lastly, we added a population scale, M1 and M2, to put all populations under the same total population so that they could affect each other directly.
For our base model, we use Locke-Voltaire's predator-prey model. The basis of the predator-prey model is that one population, the predator, preys on another population, the prey, and each population is dependent on the other. In other words, if the predator continues to eat the prey at a rate that exceeds the rate in which the prey is reproducing, eventually the predator's population will decrease as they do not have enough prey to eat. Thus, the populations restore each other in the long run. For our model, the population that will represent the predator will be the population punishing antisocial behavior, x of t, while the population that is representing the prey is the population exhibiting antisocial behavior, y of t. As seen on the right, in addition to this basic model, we applied some logistic parameters with K1, K2, K3, and K4 being the social norms that control the growth rates between the two populations. On the other hand, M1 and M2 are the population growth limits of each population. Building upon the earlier population model, we created a modified logistic predator-prey model with a shared population. This way, we could establish a direct relationship between each population and create a shared population statistic. Thus, we added the logistic expression 1 minus x of t plus y over t over M1. This way, an increase in the population punishing will cause a decrease in the population exhibiting those antisocial and aggressive behaviors, and vice versa. In addition to our three parameters, we added an entire population of non-acting people. This is because in real life, not everyone will punish or exhibit antisocial behaviors. In fact, it is more likely that there will be some sort of neutral population or people who choose not to punish or exhibit antisocial behaviors and instead be influenced kind of by the majority. As you can see in the model, we adjusted it to give outputs that are percentages of the total population. To do this, the M1 values must equal 100, and the total of the three populations at time equals 0 must add up to 100. Our third parameter is the combination of the shared population and population limit parameters. As shown in the equation above, L1 and L2 represent the minimum limits of each population. For instance, there will always be a minimum amount of those punishing or exhibiting antisocial behaviors. In our graphs that will be shown later, the effects of this will be clearer, but the specific numeric parameter for each limit will be 5%, meaning that the minimum amount of people punishing and exhibiting antisocial behaviors of the total population will total 10%, so that each population will not be negative or go lower than 0 by the end.
First, we'll take a look at how different cultures would respond to our model. Let's take a look at if antisocial behavior was encouraged. That's going to be in our leftmost graph. So we set K2 equal to 5 and K4 equal to 1. Antisocial behavior would be encouraged if K2 was greater than K4. Now, on the graph, this is a stream plot graph of all the different situations depending on the initial conditions. So if you notice, when antisocial behavior is encouraged, you're going to have the end populations be skewed toward committing antisocial behaviors. And it takes an initial condition with far more punishing behaviors to have the majority of the population end with punishing behaviors. Now, if we take a look to the middle stream plot, you'll notice that its behaviors equally spread. That's when K2 equals 1 and K4 equals 1. Now, if you look on this stream plot, you'll notice a line about in the center. So this is saying that if there's a skew towards punishing behavior, then the end result is going to be more punishing behavior. While if there's a skew in the initial conditions towards committing antisocial behavior, there'll be a skew towards antisocial behavior. And finally, if we look at the punishing behavior is encouraged, you'll notice it's the exact opposite of the first graph. For this, we set the K2 value equal to 1 and the K4 value equal to 5. Now, if you notice, it takes a very large skew of committing antisocial behavior initial conditions in order for the population to end up committing antisocial behaviors in the long run. While it takes a lot less of the population to be punishing behavior, for the long run to have the majority of punishing behavior. Additionally, you'll notice these are three-dimensional graphs, and the z-coordinate is populations doing neither, and in all cases, populations doing neither decrease. Let's take a look at an example when the cultures would be different. In our research, we found that online versus real life, the cultures would differ. People are more aggressive online, and it's harder to make corrections on that aggression. This means that in an online setting, antisocial behavior spreads faster, and it's harder to punish those antisocial behaviors. So, antisocial behavior spreading would occur at a higher rate. While in real life, it's easier to punish antisocial behavior, meaning punishment would spread faster, and antisocial behavior would be limited by that. All right, let's take a look how the equation would look like when punishing growth is greater than antisocial growth. In this case, we change the K1 value to 0.3, K2 value to 1, K3 value to 0.1, and K4 value to 3. By changing the initial conditions, we can analyze the development of these graphs. First, you look on the left, we have the population percentage of punishers at 10%, population of antisocial behavior at 35%, and population of neither at 55%. You'll notice that the population of antisocial behavior increases, and the population of punishers decreases. This is due to the fact that there aren't enough people punishing, and antisocial behavior becomes the norm, spreading and taking over both the population of punishers as well as the population of neither. Now, if you take a look at the middle graph, you'll see the initial conditions are set to 10% punishing, 20% antisocial behavior, and 70% neither. Now, in this case, the antisocial behavior starts to spread to the neither population. But additionally, the punishing behavior also spreads. Now, eventually, the punishing behavior spreads more and it discourages antisocial behavior, meaning in the long run, both antisocial behavior and neither decrease, while the punishing percentage increases. Finally, in the most right graph, you have when the punishing percentage is higher than the antisocial behavior, and again, in the long run, the punishing behavior becomes the norm. Now we'll take a look at if punishing growth was greater than antisocial growth. You'll notice we switched K1 to 0.3, K2 to 1, K3 to 0.1, and K4 to 3. Again, these are just examples of what they could be. When we take a look at these graphs, you'll notice that the punishing behavior and the antisocial behavior are just flipped from the previous graphs. So essentially, the behaviors will completely flip, and all the behaviors will be the same, except for this time, it'll be the punishers versus the antisocial behavior. In our final portion of the project, we wanted to analyze what would happen if we used reinforcement of non-antisocial behavior rather than punishment of antisocial behavior. Our source, Reinforcement and Punishment, says the most effective way to teach a person or animal a new behavior is with positive reinforcement. So in this case, we decided to have the population of punishers change to a set population that reinforces non-antisocial behavior. These reinforcers would positively reinforce non-antisocial behavior and increase that population amongst the total population. We changed our equation to x prime of t equals 0, saying that the population of now reinforcers does not change. This is a new assumption we made. We also changed the y prime equation to better fit our expected results. Let's take a look at the graphs of these equations. If we set the initial conditions to 5% reinforcers, 20% population of antisocial behavior, and 75% population of neither, you'll notice the population of committing neither increases while the population of antisocial behavior decreases. Additionally, in the second graph, you'll notice that even at a high population of 75% antisocial behavior versus 20% population of neither, the population of committing neither act increases while the population of antisocial behavior decreases. This is because people who are committing antisocial behavior will notice that those who are not committing it are being rewarded and will slowly switch over.
Overall, we found that when a population punishes another for exhibiting antisocial and aggressive behaviors, the mode of communication and cultural spread varies the rate of spread. Additionally, when applying it to the real world, online populations seem to have a higher spread of antisocial behavior, while populations that interact in the physical realm tend to adopt more punishing behaviors.
Positive reinforcements are more effective at reducing higher populations of antisocial behavior rather than punishment. This is an effective method of creating a socially acceptable environment. This concludes our presentation.
Thank you.